Good evening, everyone, and thank you for having me back. I gave a lecture yesterday to a 12-plus audience focused on the cold atom laboratory. So you can ask me some questions during the break if you'd like to at the very end of the talk, but the talk today will be focused on the future of green transportation, specifically focused on the Hyperloop, which is a technology development that I'm working on now as part of my day job as Senior Vice President of Systems Engineering at Virgin's Hyperloop One. And then I'm here in my capacity as a professor, a research professor at the University of Southern California, where I work in the Astronautics and Space Technology Department. I'm very happy to be here. I participated in the Christmas lectures, I think about 3 years ago with Kevin Fong on space exploration, and then I gave a lecture in, I think, 2016 on the exploration of Mars. So this is my third time here, and it's always a pleasure to be able to come and visit London and Great Britain. And I'm actually born in Great Britain. I was born in Scotland, and my mom actually lives up in Southport. So it's always a fun time to come here. Although I have an American accent, I do also still have a British passport. But just to give you a little bit of a background about me, my degrees are all in aerospace engineering, bachelor's, master's, and PhD, and my passion has always been space exploration. And ironically, there's a British connection there as well. When I was 6 years of age on public television, they had reruns of this very odd science fiction program called Doctor Who. And at the time, it was Tom Baker episodes that were airing, and it was actually my inspiration from watching science fiction and watching the Doctor sort of explore alien worlds and be very intelligent on everything from zoology to engineering to medicine that made me think that I would like to be like that person one day, and that's what made me become an engineer. So people are motivated by different things to become engineers. Some people are motivated by science fiction. Some people are motivated purely by the space program or try to make the world a better place, and that's essentially what I like to do with the technology that I develop. And the reason why that's relevant and germane here is that all that my passion is for space exploration and exploring Mars and exploring deep space with propulsion technologies and rovers that lands on other worlds. As an engineer and as a leader, I also have a desire to help society. And so when I was given the opportunity to help work on developing a green transportation technology solution, which is the Hyperloop, I couldn't turn that down, because if you can use your engineering skills and your leadership skills to help solve the problem, which is climate change, which is global warming, by taking a traditional, internal combustion engine type technology, whether that be related to cars or airplanes, and shift it over to something which is green, relying off of the grid power. That's one way that you can make a difference as an engineer. So I worked about 16 years of my career working for NASA on the developments of spacecraft and spacecraft technology. And so for the past year, I've been focused on the development of the Hyperloop, which is the bulk of the talk that we have here today. And that does kind of couple to this graphic, which is obviously more related to planetary science, but these three planets are actually known as the terrestrial planets. The one on the left is Venus, the one in the middle obviously is Earth, and the one on the right is Mars. And the reason why this image is very telling is that at the formation of the solar system, these three planets were actually very similar to each other in terms of having an atmosphere and in terms of having water on the surface of the planet. But right now, only we are in the Goldilocks zone, in the sense that we still have appreciable water on the surface, and we have a comfortable temperature on the surface, and we have a thick atmosphere. Mars, on the other hand, is essentially a desert planet with no appreciable water on the surface, an atmospheric pressure about 1% of what we have here on Earth. And Venus, on the other hand, has a surface temperature of 475 degrees centigrade and an atmospheric pressure of 100 atmospheres. And so something happened during the course of these planets' evolution which caused them to deviate very much from what they were to begin with. And what that means is that climate change is a planetary phenomenon and can happen for different reasons. The theory for Mars is that it experienced an impact with some kind of asteroidal body which disrupted its magnetic field because the core was impacted and shattered, and then in-space radiation ripped off the atmosphere. That's a hypothesis. And for Venus, we don't actually know what happened, but we do know that it experienced a runaway greenhouse gas effect, which then boiled the oceans, created this thick atmosphere, and created the incredibly difficult conditions for any type of life to exist on the surface today. And so, as engineers, we can help scientists make measurements to test hypotheses to understand how climate change happens, but also as engineers, we can create new technologies to solve climate change here on Earth by reducing our carbon footprint. And so this is what leads then to science fiction. the Hyperloop. And so the Hyperloop is a concept that came to a lot of notoriety in around the 2011 to 2013 timeframe because Elon Musk proposed with a white paper back in 2008 as an alternative to a high-speed rail system in California that you could use a Hyperloop instead, which would be new technology, more efficient, more cost-effective. But the Hyperloop has existed in the minds and visionaries of the science fiction world for many, many decades. And so as early in my experience as watching reruns of the Jetsons, you see people traveling through tubes at high speeds. And then some of the images that you see here are also from the science fiction literature showing you basically aircraft, or not aircraft, but craft traveling through tubes at high speed. So science fiction does serve as an impetus, does serve as an innovation for many of the technologies that we have. Great example would be the cell phone. The Motorola flip phone originally was shown by Spock and Kirk in Star Trek in the 1960s, and then in the 1980s and 1990s, the tablets that were used in Star Trek Next Generation are now kind of the technology that we use today. So even though science fiction may not provide the technological blueprint for how to make these devices, it does provide the vision of ways that these technologies can benefit society. And so the Hyperloop is another example of that, of ways that you could solve a mass transportation solution using a new technology set. And of course, it's the job of the engineer to figure out how to do that. And sometimes in life, you do get things which, as people say, well, that can't be done. Perfect example of that is, back in the late 1800s, it was said that heavier than air flying machines are impossible. And Lord Kelvin actually was the person who came out and said that. And lo and behold, you have the Wright brothers showing the demonstration of heavier than air flying machines, right? That's our travel today is basically aircraft travel, transatlantic, transpacific, over continents, all facilitated by the work of engineering and geniuses over the course of time. And it does impact our society in very important ways. And of course, for any new technology, by a show of hands, who here has seen the movie The Martian? I'd say about 50% of you. And so The Martian is a great movie. If you're an engineering fan, it actually goes to great lengths to describe the calculations which are done to show how he could survive on the surface of the planet in many different ways. But kind of the emphasis here is that you can use science and you can use engineering to get yourself out of a difficult situation. So I think it's kind of motivational from that perspective. And then my favorite quote, I would say, of all time is from Theodore Von Karman, who's the father of modern rocketry, describing the difference between science and engineering, which science is the study of what is, and engineering builds what will be. And the scientist explores, and the engineer creates the world which has never existed before. And so I think this is showing you how you can use the tools of science, the tools of math, to create these new technologies to perhaps make money, but hopefully, perhaps, to make the world a better place, and a cleaner place, and a greener place. And I think that is motivational for many people. So how does that tie into the Hyperloop? Well, just downstairs in the Royal Institution basement are a whole series of laboratories which cover the discoveries of electromagnetics and condensed matter physics, going on for the past several hundred years. And it's our fundamental physics understanding of electromagnetism which actually facilitates the technologies that go into the Hyperloop, whether it be vacuum technology in order to get down to low pressures, or whether it is a linear electric motor, which makes use of the principles of electromagnetism to be able to levitate the system and propel it forward. So it is these fundamental physics principles which have enabled the engineering solutions that you see all across the economic sectors, and specifically in the case of our Hyperloop system, or a maglev transportation system, just a maglev train, are the core behind how that's done. And with any new technology challenge, you do need to have a customer, you do need to have a reason. And so transportation has been revolutionary in our society. And so looking at that from a historical context, go back, 3000 BC is the first time that the wheel was invented. In 3500 BC, the wheel was invented for the purpose of making pottery. A couple of hundred years later, it was decided, well, we can actually use the wheel to move objects or to move chariots. And so one can only imagine how much it changed society to be able to move goods and services on the backs of chariots using wheels as opposed to not having a wheeled sort of surface. And so that was the first transportation evolution of our modern society. Move forward many hundred years later, the Industrial Revolution. The Industrial Revolution was facilitated largely due to rail service, the ability to once again transport goods and services over and across large distances, which allowed society to expand over large land masses. Move forward another about 100 years or so, personal mobility with the internal combustion engine, actually having individual cars that could be driven around, giving you point-to-point service, never has existed before. All of a sudden, you can get from point A to point B, you can connect villages, you can connect cities, you can connect states, you can connect large land masses across Europe with the means of personal mobility services. And of course, the most revolutionary one, which has happened in the past 100 years or so, is the global connectivity, which is enabled by airplane transit, which once again goes back to the Wright brothers. And so the interesting thing, though, is that we have not had a transportation revolution in over 100 years, right? Flight was over 100 years ago, and so nothing has happened since then. So now the time is right for that. But the other thing about transportation is that transportation networks can also lead to waste. So if you have congestion, that will lead to delays, and those delays can actually be translated into loss of money, right? So if you're trying to transport goods from point A to point B, and you have to sit at the dock, you have to sit at the port, you have to sit at the airport, and you can't get your goods transited, you're actually losing money. And so because money is what makes the world go round, being able to come up with a way to facilitate transportation so you can reduce those delays is really important. And then congestion, similarly, in ports, in airports, and on docks is a problem in terms of being able to get goods to be transferred. And all of these things, once again, translate into money. So if you can come up with a new technology solution which solves somebody else's distribution problem, all of a sudden you have a group of people who would be willing to pay for this new service to facilitate this new mode of transportation. And so you do need a reason, a business case, to be able to generate these technologies in other cases. And if we look at this in a little bit more detail, we can actually look at some hardcore numbers which tell us why there's a problem. There's an expected 2 times increase in port volume over the course of the next 10 to 20 years or so, right? So how are we going to solve that? We're already at congestion in the ports, and we're going to have even more goods trying to push through. Therefore, we have a congestion problem. There's an expected 80% increase in passenger miles to be traveled, and that's going to be more congestion on the roads. That's also going to be more pollution. So we need another way of getting people from point A to point B, which doesn't rely on cars. And as more of the developing world wants to have a better transportation solution, hopefully we don't want to put more cars on the road, which once again can lead to more congestion, more pollution. And then there's also an expected and anticipated 88% increase in freight over the course of the next 20 years or so. Once again, this has to be mitigated to be able to solve the problems of a growing global economy. So what is the solution? You could make a bigger airport, but that usually doesn't address the overall interoperability solution in order to make it efficient. You could add more rail lines, but if you're using old technology, you're probably going to be consuming more land, not really moving things at much faster speed. You could make wider highways. That's usually quite difficult because land availability is somewhat limited. So if you can come up with something else which disrupts this way of doing transportation solutions, that could be a good thing. And then if you look at the wider economic sector, you can take a look at other technologies which have been developed, which could facilitate a new transportation solution. And so the obvious one there is the information technology revolution, being able to transport or transmit large quantities of data over the internet, for example, over Wi-Fi, over RF. So if you have a transportation system which could be facilitated by the IT revolution, then you can have 2 things working synergistically together to improve that transportation bottleneck that we see today. So because of that, you can make the argument that now is the time for a transportation revolution, which utilizes new technologies such as autonomy and the ability to transfer large packets of information, and coupling that to a transportation system, and that's where we believe the Hyperloop can come in. And how that translates is that you want something that can operate at a faster speed, because the way that you eliminate, the time associated with the distance is to move at a faster speed. And of course, we're not talking about the speed of light, but we're talking about something which is on the order of, faster than airline travel, for example. And then you have to come back and think about what it is that your customers would actually want from you. And what everybody wants from a customer perspective is they want something which is cost effective, right? You're not going to want to have to pay an arm and a leg for something. It has to be affordable, which means it has to be in the range of airline travel or rail travel. It has to be safe. Any new transportation system which is proposed should, by definition, if reliant on new technology, should be safer than prior modes of transportation. It should have a lower environmental impact because everybody around the world today sees the importance and the need for this. And it should support larger capacities than are currently handled by current transportation solutions in order to address the congestion for both goods and for people. And so any system which is proposed has to facilitate that. And so what I'll talk about now is specifically the Hyperloop transportation system. And so in this video here, you can see an artist's conception of what a Hyperloop passenger vehicle looks like, which is what we call a pod, holds about 20 people per vehicle. Inside of it, it has a linear electric motor. That linear electric motor is its propulsion system, which allows it to go forward at fast speeds, operating off of grid-based power. And using a linear electric motor is no different from a rotational electric motor that you would have in electric vehicles. You simply spread out the platform, and you still have the same interaction of the Lorentz force to give you acceleration using the interaction of electric current with magnetic fields. The true key concept of the Hyperloop, though, is that it operates inside of a vacuum tube, which means that you reduce the ambient pressure. And so instead of operating at 1 atmosphere, you're operating at an equivalent of 120,000 feet in altitude, or about 0.1% of atmospheric pressure. All of that is done inside of a vacuum structure in which the air is removed with a series of pumps. And then finally, the element which is also of critical importance for operational efficiency is the use of a levitation engine. So you use electromagnetic forces to levitate the vehicle off of the track so you don't get frictional wear and tear on wheels as you would with traditional rolling stock for rail-based systems. And because you're operating at such fast speeds, up to 1,000 kilometers per hour, roughly 700 miles per hour, the system has to be autonomous because there is no way that a human being in the loop could operate, not acceleration, but to be able to ensure that you have, get rid of any bad safety scenarios. You have to have autonomous operation of the pods relative to each other, which once again relies on new technology. That's an artist's conception of what the system could look like, and I'll show you the video of the system we've actually built so you can see how we turn that into reality. But using new technology to improve efficiency is actually nothing new. So autonomy is being coupled to the automotive industry as we speak, and so many cars that people purchase today already have trial runs of autonomous systems where they have LiDARs on board, which allow you to detect, whether it be some kind of obstacle in your path or vehicles next to you, or if you haven't braked in time in front of the vehicle in front of you, the car will do the braking for you. So car-based autonomous systems using hazard avoidance are actually very complicated because you have many unknowns which are coming into your path. Even in this graphic, you can see, you can have a bicycle, you can have a person crossing the road, you can have an object which falls in front of you. Your car has to be able to react to that with its autonomous system for hazard avoidance. For a Hyperloop type system, you're in a controlled environment. You're, by definition, in a microclimate. And that controlled environment actually allows you to only have one directional control, and basically your hazard avoidance problem becomes easier because there can't be any people in there, there can't be any objects in there because it is that controlled environment. And then because you're operating at such fast speeds, you're enabling on-demand departure for people within the vehicles going from point A to point B and direct to destination. And so but the basic concept of a Hyperloop pod is a pressurized cabin. And so you can think of a Hyperloop pod as an aircraft without wings. And so it is a pressurized cabin because in the exterior you have a lower pressure environment. And so the pressure in the vacuum structure is about 0.1 to 1% of atmospheric pressure, and the pressure inside the passenger vehicle is about 1 atmosphere. So it has a larger delta pressure across it than a traditional aircraft cabin would have, but it's actually within the realm of possibility and easily designed using typical aircraft structures. So the way that you have to do this in a way which is cost efficient is that you have to innovate. And sometimes I worked for the government for about 16 years, it can be more expensive when you have the government innovate. So if you can use the startup methodology or the startup mentality of being very driven and very focused, using an open office collaborative environment, you can actually implement a new technology solution a little bit easier. And so there's been a lot of emphasis in media culture, at least in the United States, where you use startup environment to be able to push things forward. Whether you think about an Uber or a Google or a Facebook, those are very similar to a startup environment. So our company is very much that. We use the entrepreneurial mindset. We have a team of about 300 engineers and business strategists working in downtown Los Angeles, and we've come up with a new technology solution which focuses on the business case, which I've talked about briefly, and of course on the technology development and the implementation of new technologies to facilitate this mass transportation solution at high speeds and reasonable, affordable cost. This is a graphic you may not get since you're in the UK, but one of the difficulties associated with any mass transportation system is the cost of infrastructure, literally the cost of laying bridges, of putting up columns, and that represents a large portion of the cost regardless of what your transportation system is. So you also have to disrupt the infrastructure cost, which is very difficult. So here's my joke on the village people. Not everybody gets it. But how do you do that? You do a little bit of a vertical integration model, which means that you come up with all the prototypes yourself and the preliminary very designed for all of those prototypes yourself. And so for our company, what we did is we created a Hyperloop factory where we actually fabricate and test out welding techniques of the metal tubes which are required to create that vacuum structure. And so here you can see a portion of the steel tube that we created for our Hyperloop test facility in Las Vegas. And so when you do the fabrication, when you do the design work yourself, when you do the installation and the assembly and the testing, you actually learn how to put one of these systems together in the most cost-effective, time-efficient way possible, and then you implement that in the field for the project specifics that you want to do. And so we also created a Hyperloop test facility, and so we were able to get a site out in northeast Las Vegas, just about 45 minutes from the Strip. This was in 2016. We started to lay the column structures in place for the elevated hyperstructure, which is going to go above it. Over the course of a period of a year, we actually built a full Hyperloop system of a length of 1/2 a kilometer. And so I'll show you a short video which covers some of the work there, but we basically started off by leveling the ground, putting in the columns, then installing the vacuum structure tubes, and then installing the vacuum pumping station, and I'll walk you through that video for the next one. So here you can see a segment of tube. Here you can see the columns that are in place. You can see a rapid timeline of the columns going up. We have a mission control center where the tubes are tested. Here you can see a portion of our vehicle being built up. Once again, more of the tube in place, and Richard Branson, our chairman. And then finally, you can see our passenger pod, which is being built up. And then you'll see the final system being installed into the vacuum tube, into the site, off to the side. So this is the full facility that was built. What you see here is a 1/2 kilometer section of tube, open at the very end. The pod travels through this tube. It has a total length of 1/2 a kilometer. It spends 1/2 the portion of the tube accelerating up to speed, coasts for a little bit, and then decelerates on the other side. So you can do our speed demonstration and operational demonstration. What you also see in this image here is a pumping station. So we use commercially available pumps to get the pressure down to about 0.1% of atmospheric pressure. And the reason for that is having a lot lower aerodynamic drag allows you to go to very high speeds at a lower energy cost, which is the prior premise of the Hyperloop. And so that single pumping station can actually pump out a tube about 4 times the length of what you see here. So we built the facility so that it can evolve and grow over time. This is a pod that we developed for our test facility. So this represents probably about 80% of full scale of what we would have for our commercial production system. The unique features of the pod that we developed is we made it out of a composite, which allows it to be very lightweight, but also very strong. We also used 3D printing for the structure, which once again allows it to be lightweight, but very strong. And so these passenger pods you can think of, as I said before, as an airplane without wings, because they have a levitation engine, and they have a linear electric motor, which allows them to move forward and efficiently along the track. So this particular test program that we did, we weren't testing a pressurized pod, but the next stage of the design that we go to, we will also test a pressurized pod. But these pods are designed to carry roughly 20 people in total. And the architecture that we're using is many smaller vehicles just basically going continuously through the tubes, basically along a highway. So it's slightly different from a rail system where you would have stopping and starting along the main line. Here you would have a main line going in each direction, and people getting off for a given station would exit the main line and go to their final destination, which allows you to have a constant high speed and no deceleration in the main line, which allows you to be more efficient in terms of your energy consumption. So right here, what you see is the pod being installed into the vacuum system. And so once the pod is installed and the door is closed, the tube is pumped down to the 0.1% of atmospheric pressure. And then we use the linear electric motor and the levitation engine to accelerate it, allow it to coast, and decelerate it to do our demonstration. And whenever you do these kinds of technology demonstrations, they're done primarily for the purpose of testing out all of your models, testing out all of your designs and all of your prototyping so that you can implement that in the next phase of the design as you shift over to production. And so with all modern aerospace systems, the use of computational fluid dynamics and the use of structural modeling to be able to capture the interaction of the electromagnetic forces, the aerodynamic forces, and the electromagnetic forces. So this very last video I'm going to show you is an operational Hyperloop system that we have in Las Vegas, which is for technology demonstration purposes. So you can see the pod moving inside the tube. It's accelerating right now. Oops. You can see the other side for the nose cone view. So Our architecture here is that we go to a much higher acceleration profile for this technology demonstration than we would use in an actual system. And the reason for that is so that we can get up to peak speed in a shorter distance than you would for an operational system. So it allows us to do a higher speed demonstration in a shorter track. And to date, our maximum speed demonstration has been 387 kilometers per hour, which is not our peak speed that we intend to go to in operation, but it's the maximum speed that we can demonstrate in this length of track. And this gives you a view of what the entire track looks like in our Northeast Las Vegas test facility. And so the other interesting thing to note is that because we're out testing in the desert you actually experience extreme temperature swings, right? So during the daytime, you can get up to 120 degrees Fahrenheit, and in the evening, in the wintertime, you can get to below freezing. And so that large temperature differential happens to be an external environmental condition that is taxing on a system like this. So this technology development facility allows us to look at environmental effects as well. So the other unique aspect of a Hyperloop is the passenger experience. So if you are to travel in a rail system, you experience basically bumping along the tracks. You experience if there's any kind of, maybe small debris on the tracks, you would feel it as you're going along at speed. Similarly, in an aircraft, when you're going down the runway, you will experience bumping along the runway. When you do your initial takeoff, you'll experience higher acceleration forces. When you're in cruise in an aircraft, you'll experience turbulence because you can't control the environment that you find yourself in. The unique aspect of a Hyperloop system is that you control the environment yourself. And because the environment is essentially around the pod is a vacuum, you don't have turbulence interactions, you don't have any kind of aerodynamic interaction, so the ride is actually quite smooth. We plan to operate the system at roughly a quarter G for a maximum acceleration and maximum deceleration, which once again is within the realm of any people mover that you might take at an airport or in the realm of any metro system that you might ride in any metropolitan area. So the system itself is designed to actually be very comfortable for passengers within it. So even though you're traveling over long distances between 40 kilometers all the way up to 1,000 kilometers, you don't experience any of the traditional discomfort that you would experience in a rail system or even with an aircraft, for example. And this gives you sort of a mock-up view of the facility that we built for the Middle East so that you can get an idea of what the passenger layout is in terms of the seats. So the most important thing I would say for developing a mass transportation system is to make it reliable, to make it resilient, and to make it automated, because this allows it to be more cost-effective from an operational sense. It also allows it to have a smaller environmental impact wherever you plan to implement it around the world. And the other way of looking at this is basically shifting from a linear to a circular economy. And so a linear economy is basically where you don't have any reuse of your raw materials. You expend the raw material, it goes into waste, and then you have to reinitiate that cycle. And that doesn't allow you to be as environmentally friendly as you could be. So being able to shift over to a circular economy where your raw materials, whether it be steel, whether it be composite structures, or even whether it be batteries or the materials associated with batteries, if you can choose to implement that supply chain in a circular sense, you can actually have a smaller carbon footprint over your entire supply chain. And so that is also the goal of what we're doing with the Hyperloop, and it's the goal of many companies that are actually operating today. So that's a way of thinking about how your supply chain can tie into other supply chains so you can minimize your environmental footprint. And then I think if you think about how the system is going to be implemented, because the speeds are so fast, you can actually connect people and connect cities over a period of time, which has been unheard of before. Because at a peak speed of roughly up to 700 miles an hour and up to 1,000 kilometers per hour, you can connect major urban regions in less than 30 minutes. So from the US side of things, a very important corridor for rail transit, for example, is between Washington, D.C., Boston, and New York, which typically takes many, many hours to go between these cities. With a Hyperloop system, that new urban radius would be around 30 minutes just because of the incredibly fast cruise speed that you operate with a Hyperloop. And similarly, if a Hyperloop system were to be implemented in England between London and the north of England, you're looking at 30-minute transit times between those locations. And so it's kind of amazing to think about how this speed simply does facilitate a different way of thinking about how you can connect mega regions across the world, whether it's in Europe or in the Middle East, in India, or in America. And then for comparison, we can take a look at a system which could be implemented in the United States, where you could connect 80% of the United States in 5 hours or less. That's pretty significant, right? Being able to reach all of these urban centers in a short period of time. And even though I am not a business person by training, I'm an engineer, you can think of the induced demand, which will result in all of the areas which are now serviced by the Hyperloop, because now you can have people live there and not have to worry about the traditional, delays of traffic of being able to get from their suburban location into the urban centers where their companies may be. So how this system could be implemented in the United States is very similar to the way it could be implemented across Europe or across India or across Asia or the Middle East. And although Hyperloop does not address transatlantic travel or trans-Pacific travel, it does address travel over land masses, and it does allow you to do it in a much more green way than you can do it with current aircraft systems and with current rail-type systems because of the lower energy cost associated with operating in this drag-free environment and, of course, this low-friction environment as you're levitating the pod. So it does have the ability to connect the planet in a very different way. And every project which gets implemented will have an international consortium of partners, and those partners could actually implement those projects around the world, and they'll learn from each implementation and allow it to even go off more cost effectively in the second or third implementations. And so it is definitely a future transportation mode which is going to happen probably within the next 5 to 10 years or so around the world. So to wrap up the talk though, I think I'm a little bit over time. I want to talk about two new modes of transportation, which are up and coming, and one is flying cars. And so in my capacity as a research professor, I do research in areas of urban mobility, and so one of those is autonomous air taxis. And so there is a system that we're looking at developing specifically focused on the autonomy aspect, and so I like to go back to the Jetsons, because this is the first time that the Jetsons was shown in the context of flying cars, and show you the concept of a flying car, which essentially is an autonomous helicopter with automated takeoff and landing. So that is a concept, and they're developing many concepts around the world with different companies. And the goal here is aerial urban transport. So for some cases, a Hyperloop system is actually only valuable for longer distances because you have to be able to accelerate up to peak speed, coast for a bit, and decelerate to make the energy efficiency worthwhile. So when you're looking at shorter distance travel within urban locations, for example, or urban centers, you want to have something which is more like a metro-based system, but you could have something which is also above the ground, which is an aerial transport urban system. And because of the advances in battery technology, all of a sudden the energy densities are becoming such that you could have electrified aircraft, certainly over short distance trips, which a helicopter would need to take from an endurance perspective, but even over travel over long land masses. So by able to electrify aircraft, you can actually have a lower carbon footprint for aircraft travel, whether it be a rotorcraft or a traditional higher speed craft. And so that's a way that you can actually address urban transport in a lower carbon footprint sense. Now, the other challenge, of course, with flying is that if you have too many airplanes in the air, you can have an air traffic control nightmare and you can have safety issues. So what you have to shift over to for aerial urban transport is an autonomously controlled and scheduled system. And so that's what will facilitate being able to get more people in the pipeline in terms of whatever flight path they need to be on and then get back to their final destination. And so there's a huge amount of research going on that area in terms of autonomy and scheduling. And then finally, what you can do to eliminate ground-based congestion by getting cars off the road because of these urban aerial transport systems can actually address a lot of the safety risks associated with automotive systems and autonomy used in cars. So the very final part of the future of transportation is supersonic air travel. And supersonic air travel has existed, obviously, for fighter jets. It did exist for the Concorde, but it was not a cost-efficient way of operating, I guess, back when the Concorde existed, and so that has to be improved. And then the other challenge is that all the technologies which are being developed do still have associated with them a sonic boom, or the acoustic disturbance associated with supersonic flight. And so basically the regulations for the FAA and the regulations for any aviation authority all over the world is that you can't have that kind of acoustic disturbance over land masses, which means that supersonic flight, which is being proposed, is still limited to basically over the water travel, which doesn't represent the bulk of long distance travel and also requires you to go subsonic before you actually approach areas where people are living. So that happens to be a technology limitation associated with supersonic air travel because of the restrictions associated with people not wanting to be disturbed by a sonic boom, which makes sense. And so that basically prevents supersonic flight over 70% of air travel, right? Because of the fact that you can be limited over water, so it's only good for transatlantic, transpacific for a portion of it. You have to have a system really to be able to be autonomously controlled. Same thing for Hyperloops, which have to operate at high speeds. You also have to have aircraft operate at these high speeds, also autonomously controlled. You can still have a pilot in the loop, but you probably don't want to have 2 or 3 pilots in the loop. And if you take a look at the projections of how many pilots there exist today, there aren't enough pilots now to support the amount of air traffic which is planned. So being able to shift airplanes over to autonomy also makes a lot of sense. And so that's where we're headed with supersonic travel. And so one of the research projects that I'm working on at USC is actually the design of a new aircraft, which does have a technology solution to reduce the intensity of the acoustic disturbance that comes about as a result of the sonic boom, which is generated by the supersonic environment. And although it is IP restricted, the goal is you can come up with a wing geometry, a wing curvature, which interacts with the exhaust plumes of the engines which are providing you with your thrust in order to mitigate that disturbance. And the interesting thing is there is an analogy from the Mars program where the Mars landing systems actually have engines which point towards the ground. They have supersonic exhaust plumes, and depending on how you design the curvature of the nozzle and how it interacts with the ground beneath, you can actually dissipate a lot of the energy in those exhaust plumes. So there is a large area of research possible between the aerodynamics of the wings and the interaction of the aerodynamics coming out of the exhaust plumes, where you can help to mitigate that sonic boom, reduce the overall acoustic disturbance, and then get it to levels which then allows you to fly within limits the FAA imposes or whatever the British authorities or European authorities would impose on people. And so that actually would facilitate the use of supersonic air travel in that case. And so that's one final aspect that we're working on, and we did a 3D print of the vehicle. Now, the good news is that you don't have to build the aircraft and fly it to make sure that it works. You can use computational fluid dynamics. And so when you're operating a supersonic regime, it is a little bit more of a difficult regime to be able to capture the interactions in, but modern day techniques, looking at turbulence and having good models for turbulence enables you to get those get the performance that you need out of the wing and show ahead of time that it works. You then make a model like this for a wind tunnel. You wouldn't make it out of plastic, you would make it probably out of metallic, and then you would validate your computational fluid dynamic simulations by testing the model in that environment to show that it works. So this, I would say, is going to happen in the next 15 to 20 years, but the far future is slightly different. So the far future, I do believe, is going to take us off of planet Earth and send us to other locations. And so I believe what's in the far future is for humans to travel in space. And I think what you've seen over the course of the past 5 to 7 years or so with the advent of SpaceX, Blue Origin, Sierra Nevada, are companies who are developing lower cost access to space and then developing vehicles to be able to get you from Earth to Mars and then eventually land you on the surface of Mars. So this particular vehicle, which is being developed by NASA, the Orion program or the Orion capsule, is intended to take human beings into deep space, whether that's to land them on the surface of the moon or send them all the way out to an asteroid or to land them on Mars. And so, whether you agree or like space travel, there are many people who are interested in it for commercial purposes, for space tourism purposes, and so there's a huge shift in the transportation sector to develop space-based technologies to enable people to live on other worlds. There's a whole set of challenges associated with that. A lot of them is associated with the energy cost of being able to defeat Earth's gravity well, but then the other, of course, is being able to slow down and land safely on the surface of another world. And then after you get to the other world, the next important thing is to be able to survive there and set up colonies on other planets. And so there is work being done now at NASA and space agencies around the world to understand what kind of life support systems are necessary to port yourself on the surface of another planet. And this is an example of a habitation module which is being tested to show that human beings can actually live safely on the surface of Mars, not from the perspective of looking at the radiation environment, but from the perspective of how are you able to regulate how much water you consume, how are you able to grow your own food, how are you able to provide that sort of closed loop system so that you can survive for periods of 9 months to 2 years on the surface of another planet. And so all the technologies, we have to do a much better job of how we're doing it here, actually, at that point. And that leads to the very final point, which is basically in situ resource utilization. And so we've all thought about recycling, right? We take our, if we compost, we're able to return our plant matter and make it into soil. If we recycle our metals, if we recycle our plastics, we're able to put it back into that pipeline. But ultimately, if you're going to travel to another world, you actually have to use the resources on that other world. You can't bring everything with you. And we kind of have to do that here here at home. And so one of the ways that you can tie this into a rail type system or a Hyperloop type system is to utilize solar panels, right, on the exterior of the tube or on the exterior of the track where the system is going. And so there is a desire to be able to implement that type of closed-loop powered system for a Hyperloop system in the near future. And if you can somehow couple that to, you know, in some cases where you don't have solar panels, the use of trees to shade, to have a more regulated thermal environment, that's something that we should also consider. But in situ resource utilization, for going to the moon, for example, even the Apollo astronauts used that. They actually filled bags with sand, put it over where they were to provide additional radiation protection. The same thing could be done on Mars. But that's something that we have to think about. Our mindset essentially has to change as we get to the fact that we're hitting, you know, the edge of what we can handle in terms of fossil fuels and in terms of what the impact is on climate change. So all the technologies that we're looking at today, whether it be a Hyperloop, which is using grid-based power, which hopefully is coming from renewables, whether we're looking at autonomous air taxis, which are using electrified batteries, which get their power from grid-based power, which can come from renewables, or for supersonic planes, which eventually could be sort of a hybrid system of having electrification for some of the power, but still a backup of a internal combustion engine, are ways that we can have a greener, more efficient future for transporting ourselves around the planet. And so the very last thing I wanted to talk about today is women in STEM. And so I was able to work on a book with Libby Jackson. It's called Galaxy of Her Own. She's from the European Space Agency. She's an engineer there who works on mission operations. And in 2017, she released a book here in the UK and Europe, and then she released it in the US under a different name, which is Galaxy Girls, which is the story of 15 women and their roles in the space program. And for any of you who have daughters or young women in your life who might be interested in studying science or engineering, this is a very inspirational book, and it has basically the stories of 15 women from, you know, Sally Ride to Mae Jemison, to all of the most recent astronauts are all in this book. And I do encourage you to consider getting a copy for your local school or your local library or the women and the girls that you have in your life, because it can be quite inspirational. And that is something which is important to me. And as I go around giving public lectures on the topic of the Hyperloop, on the topic of space exploration, I always like to encourage people to think about how they can take what they've learned in these lectures and spread it to other people in their lives. But for the last, I guess, 15 minutes or so, I can take questions from the audience. So, and I will actually try and find that graphic that I was missing before, too. So thank you.